So let's switch from the bullet soft to the hard pin constraint, and let's hit play, and we'll get this result. Now again, there's no damping, there's nothing happening to how the pieces are behaving. And one thing that is overlooked is the RBD objects properties. There is one called rotational stiffness. Okay, and a couple of versions back, this option, or let me rephrase it. When we create the data, like we did here inside of SOPs, inside of DOPs, we're using a SOP solver to emit RBD objects. These objects that we're initializing, they don't have all the properties and attributes needed for bullet, but it's using the default, so we're only providing it with the ones that we want to control. When we create this object, it initializes everything needed for bullet. So if I do allow editing of this node and dive inside and go inside the which one, yeah, create this one, create or override attribute. So here you can see there's multiple attribute create nodes, and they all set up all kinds of properties that bullets is looking for. Okay, and this is the best place to know the attributes and to get the see the names of the attributes themselves. And one of them is called inertial tensor stiffness. This guy. Okay, and this is the rotational stiffness, which is here. So let me do another example with it set to 1. So this is our original example, and I'm going to change it to 10. See, now it has more resistance. That we're not changing the constraints or anything. We're changing the RBD objects. See, now it's even more, it's stiffer, it's harder to deform. And let's set this to 1000. Now what if we can copy the constraints information? We have that angle attribute from the constraint. What if we can copy that back into the geometry, okay, and use it to drive the stiffness? Now a couple of versions back, this attribute was locked to only be initialized once. Okay, we cannot change this using a SOP solver. And in the recent version, in I believe Houdini 17, we can post-process these guys and change the values. So what I'm going to do is I'm going to create a SOP solver, and we're going to mess with this data. So let's connect this guy. And now we have access to the RBD objects. I'm going to create a wrangle node, and I want to change that initial tensor stiffness. If we hop over here, it will show us the attribute name. It's called what I just said. The name is too long. Initial tensor stiffness, or inertial tensor stiffness. Okay, let's go up, copy that name, and then let's come here, and I'm going to say it's a float, and it's equal to 1000, and let's see what happens. It's working. So we're changing this value using this SOP solver now. And what I'm going to do is I'm going to go to the SOP solver where we had the constraints, and I'm going to copy this node that we're using to import the constraints, and I'm going to import them inside here, okay, inside this SOP solver where we're changing the stiffness. And let me copy one more thing. I'm going to copy this code here, and what I want to do now is, this is the code that we're using to copy the transform matrix from the packed primitives onto the constraints. We want to do something different now. We want to copy to the RBD objects, okay, from the constraints. What we want to copy is this angle guy. And again, the name to point. So each RBD object is going to look up the name that on the constraints, give us back the point, and we're going to read an attribute now. We're not going to use the prim intrinsic because we just need to read this guy. Okay, and we don't have a primitive information. We have only point number. So what we need to do is we need to promote that attribute, that angle, from primitive to point. And I don't want to delete it. I want to keep it. I'm going to change its name to angle PT. And now we're copying this to the point level, and I'm going to plug this in. And here I don't need this prim intrinsic. I'm going to use the point expression, and I want to read angle PT, and the point number is this. And also this is going to be a float angle. Okay, so now we're creating this float angle. We're copying it from the constraints into the pieces. Let's take a look at one frame. See this angle here. So it's really low. I mean, even these guys are low. And we're gonna remap this. We're gonna use this angle information to, let's say, if the angle goes between 0 to 0.001, we want to remap that so that it drives the inertial tensor stiffness to be from 1 to 1000. Okay, so in here I'm gonna, instead of setting a constant value, I'm gonna say fit this guy, which is the angle. I want to fit it, and its input range is between 0 and 0.1. We're gonna start with that, and I want to fit it between 1 to 1000. Let's put 10,000 just so we can see the difference clearly. What's gonna happen is, as the angle gets higher, the stiffness is going to get higher. Okay, let's see, it's doing something. And let's lower this even. Let's lower that. I'm gonna set it to 1000 only. 10,000 is high. And you can see now as it bends, the rotational stiffness is holding up. Okay, there is resistance with the hard pin. It's not. We're creating this stiffness now. And now if we turn back on our deforming, the thing that deforms the hard pin constraint, we're gonna get something that holds itself up like this. Okay, now because of the shape, because of these boxes, we need to test it with actual RBD geometry or actual Voronoi pieces to see how that looks. So let's make this bigger, wider. I'm gonna make it thinner, and let's fracture it using the previous setup. Okay, and everything is the same. And just to be clear, this is just an idea that we could try. I'm not saying that it's going to be perfect or anything. I want to show you guys how we can do the inverse of taking something from the constraints and changing an attribute on the geometry itself. So this is how it looks like. Okay, let's add one more thing and see. Let's turn on the deletion to get some breaking happening and see how that looks. Yeah, it's working, and there's a lot of potential here. And I think if we mix this with the technique that we did before, actually I will do it just now. I'm getting some nice deformation for sure. So let's go up and let's mix the constraint. So instead of everything being pin constraint, I'm gonna mix them. And let's turn back on the glue constraint as well. So let's merge this with our glue constraint. let's see what we get. Not enough data to rotate, but I think you guys got the idea. So let me lower the rotational stiffness to 200. Yep, we're getting a perfect crack here with a lot of details, and I definitely think there is value in this method. You can see it's holding up as well, and we got the dampening now. It didn't just bend in a linear fashion. There is a resistance to it. Okay, so that's basically the idea here, and there's so many things we could do with this. I want you guys to understand that it's possible to change the RBD data using constraints. It's not just the constraints that we want to change using the RBD. And just to be clear, I haven't used this technique yet, but it could be very, very useful with the metal bending. I'm going to show that in a later week, and we could get metal denting really easily with this setup, but the main challenge is the tearing of the metal. If we want to get that's much harder, because let's go back. I'll show something here. So I'm going to copy this, and I want to fetch the transform geo, and this is the geometry. I'm going to fuse it. Okay, and I'm going to use a point deform, and I want to deform this geometry with these guys, and this is going to be, this is the deform, time shift to 1, and this is the rest. I'm waiting for it to sim. Cool, so let's set this to 1. Set this, yeah, something like this. Okay, I mean the input geometry is not perfect, but this is how you get the metal deformation. Right now we have fracturing in the geometry, and that's why we're getting these weird shapes. But if it was just deforming, we could generate a very clean mesh that has the denting look or the metal deformation in it. But again, the problem is with the tearing. If we want to start introducing that's going to be much more challenging to get. And I'll show a prototype that could work in various scenarios, but we'll leave that for a later week. And I think that's pretty much it. Hopefully this covers all ideas related to the soft spring and rotational stiffness. Thank you guys for watching, and see you in the next one. Bye bye.